Hey everybody, welcome to lecture 5.4 on the gradient vector. In this video, we're going to take our knowledge of vectors from the last few sections in chapter 5 and pair it with multivariable calculus to produce something called the gradient vector and related to this directional derivatives. And together, these will be a more sophisticated way of measuring rates of change for multivariable functions, meaning functions of two input variables or more. We'll start by understanding things in 3 dimensions where there are 2 input variables x and y, and then the output variable is thought of as the height z. And this will also work in higher dimensions than that. The main goals we want to tackle in this video are to compute the gradient vector of a function. We'll define it first as a particular vector with components given by the partial derivatives of the function, and then we'll learn how to compute that. We will relate the gradient vector to the shape of a graph and its level curves. And this is really where the gradient vector has a lot of power. The most satisfying interpretation, in my opinion, and I think will be a good visualization for all of us to keep in mind, is something like a topographical map, which is how we visualize level curves. And you'll see this thumbnail we've seen before show up a couple times in this video. On a topographical map, if we view that as the level curves of our function, the gradient vector will tell us the most efficient way to travel uphill or downhill. And that's essentially the most powerful interpretation of the gradient vector we'll see, but we'll have a few different ways of utilizing it through the course of this video. Finally, we'll define and compute directional derivatives. We'll do this sort of at the same time we talk about the gradient vector. And directional derivatives, again, will be a more sophisticated way of measuring rates of change that aren't just in the direction of the x or the y axis, as we've done previously. So to get started, here's a question to get our minds running on multivariable calculus and why we might use something like a gradient vector. How do we compute rates of change that aren't just in the x or y direction alone? Remember that partial derivatives are computed by holding one of the variables constant. In this case, if we hold y constant, we would let x vary and compute the x directional partial derivative, or vice versa. These give instantaneous rates of change, but we might be interested in rates of change that are not just parallel to one of the axes, but instead could come at an angle, or in other words, along a different cross-section of our surface. Geometrically, slopes of tangent lines could happen in any direction, and in fact, all possible slopes of tangent lines will be described by the slopes of lines lying in the tangent plane to the surface, which we learned about last chapter. So if we want to travel in a different direction than parallel to one of the x or y axes, we want a numerical or algebraic way of computing that rate of change, and this is done using directional derivatives. So we're going to define directional derivatives for a function of 2 variables x and y, but this definition actually works more generally. We'll talk about this a few slides later. So let's start with a function f of x and y, and we're going to choose a direction in the xy plane to travel, or in other words, a direction in the domain of the function to travel. Since traveling in a direction doesn't depend on the length of the vector we choose to travel, we'll just choose u to be a unit vector in the xy plane. And remember that a unit vector is a vector of length 1. So if we choose a point in the xy plane, let's say x comma y, and a unit vector to travel along, this in fact uniquely specifies a tangent line to the surface z equals f of xy, and the directional derivative in words will be the slope of that tangent line, or the rate of change of the function f as we travel in that direction. So these are two ways to think about this in words. It's the instantaneous rate of change of the function as we travel along a vector in the domain of the function, or equivalently, it's the slope of the tangent line to that function in the direction of this vector. Those two things are equivalent by single variable calculus. It will be interesting in a moment to come up with an actual formula, and we'll have 2 different formulas for computing the directional derivative, but this is what it means in words. I want to give you one more interpretation. You can think of this as an alternative definition of the directional derivative at a point. And this is done by cross sections. Remember that the partial derivative of the function f of xy, let's say in the x direction, can be computed by taking a cross section of the surface z equals f of xy that's parallel to, if it's the x partial derivative, it'll be parallel to the xz plane. So it'll be a vertical plane that we slice our figure with. That will trace out a cross section, which is some curve, perhaps shown in the teal color here in the picture. and that curve has a tangent line. That tangent line slope is the partial derivative in that case. If we take a different cross section by another plane, which for our purposes in this lecture will always be a vertical plane, but may not be parallel to one of the coordinate planes, the XZ or the YZ planes. If we take some other vertical, but not necessarily coordinate parallel plane, this will slice our figure into a new cross section, and the corresponding teal curve will have a tangent line. The slope of that tangent line will be the same thing as the directional derivative through that point. So those are a few different interpretations. We're really interested in computing directional derivatives to measure rates of change in multiple variables. And if we use the partial derivative definition as inspiration, we can come up with the following definition called the limit definition of a directional derivative. So remember that I'm going to use capital D notation, dxf, because the notation for a directional derivative also has the capital D notation. So if you remember that the partial derivative dx of f can be computed by taking displacement or taking a change in the x direction and taking the limit as that change goes to 0 of the slope of the secant line. This is the formula that we studied before. So the partial derivative of f with respect to x is given by the limit as we change x a little bit in the numerator and plug them into the function and divide by that amount we changed by. This is a slope of a secant line, or equivalently, the slope of the tangent line through the curve defined by the cross section holding y constant at that point. There are a bunch of different definitions. So let's use the exact same approach to define our directional derivative along a unit direction u, which in the slides is written ai plus bj. Remember, that just means that the displacement coordinates of u are a comma b in bracket notation. And we want to compute in that direction the rate of change of the function. So what we should do is vary our point x comma y that is in the domain of the function by translating by this vector by some small amount, and then shrink the amount that we translate by down to 0. The way to do this algebraically is to take the point xy and add to it some small amount t times our vector. And if you add the point xy to t times our vector and write out the new coordinates of this point, it'll be x plus ta. A is the x coordinate of the vector u, and y plus tb, where b is the y coordinate of the vector u. So this is a point that is some small distance away from our point in the direction of the vector u. And if we apply the exact same approach we did with partial derivatives, we will take f of that new point nearby minus the f of xy value, the height of the function at the point, and divide by that small amount that we moved away. Since u is a unit vector, this really is displacing by t and dividing by that amount of displacement. And my dog's growling at some dogs outside, so if you give me one moment, I'm gonna All right, always the fun part of being a dog parent. So anyways, this is our limit definition. It's inspired by our limit definition for partial derivatives. Sorry, 1 second again. All right, I think that'll be the last one. By the way, I hope you enjoy the random interludes with my dogs, because this is my life. And yeah, it's fun to talk about them. I should really bring them into class sometime, but I don't know how they would do with people in a big scary classroom they've never been to before. Okay, so as I was saying, we have a limit formula for the directional derivative. And I don't know about you, I don't like computing limits if I don't have to. So shortly we'll see an alternative definition of the directional derivative du f of xy. But for now, this is the definition that we have. So you can go and compute with this to practice in certain examples. Here's some questions that I want to pose that'll get us thinking about applying the directional derivative, and ultimately will lead us to the study of the gradient vector. These are just some natural questions you can ask about a function of two variables. So now that we know the directional derivative can measure rates of change in any direction in the domain of the function, we can ask which direction, if we're allowed to swing in 360 degrees around our point xy, which direction produces the greatest derivative or the greatest rate of change? And likewise, which direction will produce the smallest rate of change? we will see that these are related to geometry. So I want you to start thinking about how these directions of maximal and minimal rate of change are related to the geometry of the graph. And specifically, if you can visualize things using the plot of level curves, how do those vectors relate to the level curves? And finally, how do these directions relate to the partial derivatives that we've already studied? In the slides, you'll see that there is an interactive widget that's linked. Or actually, this might be linked in the textbook. I apologize if I said that wrong. But there's an interactive widget where you can actually play around with these rates of change by swinging your vector into different directions and trying to identify the direction of largest or smallest rate of change. If you play around with these graphs a little bit, and here's an example. Here's just a screenshot of one example of a graph and fixing a direction. This little purple vector here is a unit vector v starting at the point 2, 1 in the domain of this function. And the slope of the red line will give you the, so the red line itself is a tangent line in the direction of u in the domain, and the slope of the red line will give you the directional derivative in that direction u. So if you play around with this, there's some sliders in the interactive version. You might come to the following conclusions. And I'm going to give these just as facts. There's actually some math involved in verifying all of these things, since we started with, or we're going to start with the following definition of the gradient vector, and then the following remarks will be facts about the gradient vector that I'm not going to prove in this lecture, but you can look up yourself. So first of all, the gradient vector is a vector attached to a point x, y in the domain. And it's a 2-component vector, so it's also a vector living in the xy plane. But that vector is the vector whose x component is the partial derivative of x with respect to x of the function f at the point xy, and whose y component is the partial derivative of f with respect to y at the same point. So said more succinctly, the gradient vector of f is a vector whose 2 components are the 2 partial derivatives with respect to x and y, respectively. Just as a heads up, we're going to generalize this to higher dimensions shortly, but this is the 2-dimensional version when our function has 2 input variables, x and y. By the way, the symbol you see here is pronounced nabla. I believe it's a Greek symbol. It's not one of the Greek letters of the alphabet, but it is a symbol in Greek script. And if it's not Greek, I should have looked this up ahead of time. You can ask me in class. I believe that it's, if not Greek, then it's Cyrillic. So in any case, it's Nabla, N-A-B-L-A. And if you want to learn how to type this, you can Google how to type the Nabla symbol. Again, N-A-B-L-A. So the gradient vector is a vector whose components are the partial derivatives. We can evaluate this at different points in the domain of the function and get different vectors. So you can really think of this nabla of f, this gradient vector, as a function of x and y that has 2 components. This is really what's known as a vector valued function, which we haven't studied previously. But it's a function that has an x and a y component, each of which can possibly depend on the x and y input variables. So different points have different gradient vectors. And what's useful for us is that the direction that maximizes the directional derivative. So there's some direction vector u, a unit vector, which we'll call u max, which maximizes the value of the directional derivative, or maximizes the rate of increase of our function, turns out to point in the same direction as the gradient vector. We're going to give a proof of this shortly because it's worth seeing how this actually works. But for now, the gradient vector is a direction that tells you the maximum rate of increase away from your point. And again, this will depend on what point x, y we plug in to the gradient vector. On the other hand, the direction of minimal increase, which, the notation isn't very consistent, but u sub 0 is what the book uses, the direction in which the directional derivative is minimized will turn out to be tangent to the level curves. And if you think about it, along a level curve, the height of the function is not changing, so it makes sense for that to be the minimal rate of change of the function. And a tangent vector to one of those level curves should give you the direction of minimal increase. This turns out to be orthogonal to the gradient vector. The way we'll see this is that the gradient vector is orthogonal to any level curve, and intuitively, level curves are the directions of minimal increase since the height doesn't change along those. So that's a lot to unpack. Let's try to visualize things a little more. So tangent lines in general, these are the lines whose slopes will be measured by the directional derivative in that direction. Tangent lines in general live in the tangent plane, which we defined in the previous chapter. We will have a new formula for the tangent plane in this lecture. So we're actually learning a whole bunch more about geometry and tangent planes. We can compute the slope of a tangent line in general using rise over run. That's what slopes are measuring in general, a rate of change of one variable with respect to another. And in this case, if z is our output variable, we want to measure the rate of change in the direction of u as follows. So let's let z again be the output values that in this case will take on values in the tangent plane if we use points nearby and their heights on the tangent plane. If we have a unit vector starting at our point x naught comma y naught and stretching one unit away to some other point x1 comma y1, and we let the corresponding heights of these points in the tangent plane be z naught and z1 respectively, then the directional derivative, which is the rate of change of the function in the direction x1 comma y1, or rather the direction u, which is the displacement from one point to another, can be given as rise over run, or the change in z divided by the change along that vector, which is also known as the length of the vector. Since the vector is a unit vector, this is, in other words, the length of the vector is equal to 1. We just have a displacement z1 minus z0, which can be measured by moving in the tangent plane in the x direction followed by the y direction, or vice versa, since these can be done in either order. So to move in the x direction, the rate of change of z can be computed essentially using our differential formula, which I'm going to write using partial derivative notation. You can think of this as fx dx plus fy dy, which gives us our dz. And in this situation, fx and fy are really the two components of the gradient vector. Whereas x1 minus x0, y1 minus y0, those are actually the components of our unit vector telling us which direction to travel. So if we realize this differential formula instead as a dot product of two vectors, that's secretly what we did here. First components are multiplied, the second components are multiplied. Then the directional derivative can be computed by taking the gradient vector at our point x naught, y naught, and dotting it with the unit vector telling us which direction to travel. So again, this is a new formula for the directional derivative. It's a little easier to work with than the limit formula a couple slides ago. And the formula says that the directional derivative in the direction of u of our function at a particular point x naught, y naught is equal to the gradient vector at that point dotted with the unit vector of direction. Let's generalize things now to higher dimensions because we have everything we need to say this, and then we'll study some examples to close out the video. So if we have a function of a larger number of variables than 2, for example, f of x, y, z, or in general, f of x1 through xn, as long as this is a differentiable function, meaning we can compute the rates of change in any direction, then we can define directional derivatives along any unit vector in n dimensions. So if we start at a point x1 through xn that has some coordinates in n-dimensional space, and we choose a unit vector to travel 1 unit away from that in any direction, we will let du of f denote the directional derivative of our function f in the direction of that vector. And we can define this algebraically using a similar limit formula where we change the coordinates x1 through xn by the coordinates of u times a small parameter t and shrink t down to 0. But more usefully in higher dimensions, rather than computing a complicated looking limit like that, is to define the gradient vector, which will be an n-dimensional vector whose components are each of the n partial derivatives of f with respect to each of those n variables. And we can instead define the directional derivative duf to be the gradient vector dotted with that direction vector. Now, again, this is the nabla f, the directional, or the gradient vector in this case, is a function, each of whose components is a function of all n variables. So it's a vector valued function. And if we choose a particular point x1 through xn and plug it into this part of the formula, we will get a vector. The vector u is specified for us, and then we'll end up getting a scalar or a real number as an output. That will be the rate of change of the function in the direction u. This is how to do things in higher dimensions. We will actually have use of functions f of x, y, and z, and their directional derivatives and gradients by the end of the video. So I just wanted to introduce this now. So let's get back to our questions about rates of change from earlier. We have a formula for directional derivatives, and the claim a few slides ago is that the gradient has something to do with the maximal rate of increase of the function. And also level curves are perpendicular or orthogonal to the gradient vector. And finally, we want to ultimately maximize the directional derivative in terms of choosing a direction and then computing the directional derivative in that direction. So how do all of these things fit together? Well, the following 4 steps will step us through a discussion of these concepts, and we'll ultimately arrive at an answer to each of these 4 questions. So I'm going to switch over to the tablet. We're going to take a bit of time to do these together. If at any point you want to pause the video and try to answer those questions yourself, you can rewind a little bit or go look at the slides that are uploaded on Canvas and see those 4 steps. But I'm going to have a bit of an interactive discussion here where some parts are filled out and some parts are not. So in part A, we're going to start by expanding our dot product formula for the directional derivative in terms of an angle theta between 2 vectors. So let's start by rewriting our algebraic or dot product formula for the directional derivative. Remember, f is some function of x and y, and u is a unit vector in the xy plane that starts at some input value for our function. So we learned a few slides ago that the directional derivative can be computed by a dot product of the gradient vector nabla of f at that point, dotted with that unit vector u. And if you remember from the dot product section in the previous chapter, or sorry, the dot product section in this chapter, the dot product between 2 vectors can be computed in terms of the angle of the vectors as follows. So if we take the lengths of these 2 vectors and multiply them, and then further multiply by cosine of the angle, where cosine is the angle between nabla f and the direction vector u, then this is another way of evaluating their dot product. So this tells you how to compute the directional derivative. We can go one step further because we know that the unit vector has length 1. So let's simplify this by writing that the directional derivative in the direction u can be computed, if we so choose, as the length of the gradient vector times cosine of theta, where theta is the angle between the gradient vector and the direction vector u. This is the key piece of the puzzle to understand all of the questions we've been asking so far. For example, if we want to find the direction of maximal rate of change, in other words, we want to maximize this directional derivative, we can just look at this formula and ask what theta will maximize our quantity here. If we fix our point x comma y, then the gradient vector is fixed. So this length here already has a known value. And we're only allowed to change the direction u that we travel to change our rate of change. So let's answer this question now. In which direction will u increase fastest? Well, we just saw that the directional derivative, which measures rate of change, can be computed by the length of the gradient vector at xy times cosine of the angle that gradient makes with our direction u. And this is maximized when, well, the cosine part is the largest it can possibly be when cosine equals 1, or when theta is equal to 0. So geometrically, when 2 vectors, let me rewrite that a little bit, I wasn't happy with that 0. Geometrically, 2 vectors have an angle of 0 exactly when, and this is where I want you to pause the video and think about this for yourself, but I'm going to answer it now. 2 vectors have an angle of 0 when they point in the same direction. So let me write this out in full words. If the gradient and the direction point in the same direction. This actually is something that I alluded to earlier, it was one of the remarks under our definition of the gradient vector that said the gradient vector points in the direction of maximal increase. We have now seen this to be a fact. The gradient vector is pointing in the same direction as the direction u that maximizes the rate of change of the function. And we can even do one better. The direction in this case is a unit vector u, and it points in the same direction as nabla f, the gradient vector. And we know that a unit vector in the direction of another vector is always given by take 1 over the length of that vector and scale the vector by that quantity. So this is a formula for the direction to travel, or at least a unit direction to travel, to get the largest increase in your function, or to try, in other words, we'll see on our topographical map later, to travel steepest uphill or travel uphill fastest in our three-dimensional graph of the function. And this is a formula for that direction as a unit vector. If you just wanted some vector in the direction of maximal increase, that answer is always going to be the gradient vector, which confirms something we said earlier. Next, what will be the value of the directional derivative in that maximal direction? We actually want to know what the maximal rate of change is in terms of the point x comma y and probably some partial derivatives of the function. So let's take a step back and repeat our the results of our dot product formula in terms of the angle. What's going to happen here is that if theta is equal to 0, we saw that that was the angle that gives us our maximal increase. Then cosine of 0 is equal to 1. So the directional derivative in the maximal direction has value the length of the vector nabla of f, the length of the gradient vector. So this is showing why the gradient vector is actually a really powerful tool for us. It is a vector, so it has a length and a direction. Remember, those are the key pieces of information in any vector. The direction of the vector nabla f tells us the direction to travel to go uphill fastest, or to increase our function in the fastest way. And the length of the vector, that gradient vector, tells us the actual rate of change in that maximal direction. So it tells us all we possibly need to know about rates of change of our function, at least if we're trying to maximize that rate of change. Let's answer the other question, which was what's the minimal rate of change? And to do this, I want to rewrite our formula from above one more time and answer the question, in which direction will we get a directional derivative of 0, meaning a minimal rate of change, or no rate of change, in other words. If we rewrite using our angle formula, the directional derivative is computed by the length of the gradient vector times cosine of the angle between the gradient vector and our direction u. And if we set this equal to 0 and try to ask for which angle this will happen, cosine of theta, and let's assume that the directional derivative is, and sorry, I said direction. I really need to say the gradient vector, nabla f, is not the 0 vector, so it's actually pointing in some direction here. At such a point, that means that cosine of theta has to be 0, and the only place in the domain of arc cosine that solves this equation, or the place in the top half of the unit circle that gives cosine of theta equals 0 is, and again, you can pause if you want to write this for yourself now, but let me answer it for you. It will be pi over 2, or a 90-degree angle. If we interpret that geometrically, this says that the direction u of minimal increase and the gradient vector are perpendicular, or at a 90-degree angle to each other. So we just learned two things. The gradient points in the direction of maximal increase of the function, and the length of the gradient vector tells you that amount of maximal increase. And on the other hand, directions perpendicular to the gradient vector will be of minimal increase, or will have directional derivative equal to 0. So no rate of change along those. I'm not going to prove this part, but I want you to go back and think about how level curves therefore have to be perpendicular to the gradient vector. That's one extra piece of information that we just learned. So returning to the slides, let's learn even more about rates of change and directional derivatives. Here, by the way, is a picture just in the xy plane of our point x and y, the direction that we're going to travel to compute a rate of change that's given by the unit vector u, the gradient vector, which the components of which are the two partial derivatives of our function f at x and y, and then the angle theta made by these two vectors. If you imagine swinging the vector u, which you're allowed to change, around to point in the direction of nabla f, the gradient, you will maximize the rate of change in that direction. And in this case, for this particular example, I believe this is the three-dimensional graph shown in an earlier slide. The directional derivative at this point is given by some number 1.43, and as you slide u around using the interactive widget, you'll see that the value approaches the length of nabla f, which is 1.94. So here's just a quick review, since we're learning a lot of topics in this one video. The cosine formula for the dot product allows us to relate directional derivatives to an angle, and using our knowledge of angles and how to maximize and minimize the cosine function, we are able to learn about which directions give you a maximal or minimal rate of increase of your function. And in particular, the function f of xy increases fastest when we travel in the direction of the gradient at that point x comma y. And on the other hand, the rate of change is slowest, or is equal to 0, in fact, when we choose a direction that's orthogonal to the gradient vector. Here's an example where we can put all of these things to work. Here's a function f of x comma y given by this formula. And we've already chosen a direction, 0.6, negative 0.8. We're going to ask some questions relating this directional derivative to other directional derivatives, and we'll make use of the gradient vector because it helps us compute the directional derivative. But I also want you to think about geometrically what the directional derivative along the gradient vector will tell you. And I'm going to switch over to the tablet to work through all 4 parts of this problem, but I encourage you to do this one on your own, at least parts A and B. Part A is a review problem for sketching level curves, but it's going to help us answer parts B, C, and D. So as I switch over, I'm going to take a drink of water. And then let's get started. So in part A, we're asked to identify the level curves of f. I left a little space to sketch these to the right, but algebraically, you might have a guess just by looking at this formula. But algebraically, it makes the most sense to set the formula for f of xy equal to some constant k, and then try to do our best to solve for xy, or at least come up with an equation that looks familiar so we can sketch it and talk about it algebraically. So I'm going to square both sides of the equation. And I've had some practice with this, and you might have already practiced with similar examples. I see this as a circle equation. Explicitly, if I solve for x squared plus y squared on the left side, I'll have 9 minus that constant squared on the right side. And this is a circle of radius square root of 9 minus k squared. I don't know what that is in general, but if I pick a few values of k, we can actually graph this. So for k equals 3, and by the way, I only want to choose k non-negative, since I can't have the square root symbol equal to a negative number. That'll have an empty level curve. But for k equals 3, for example, plugging in 3 will give me a radius of 0. I'm just going to label these with a small number for their height. That's the k value. That'll give us just a trivial circle at the origin. If I plug in, let's see, k equals, oh, what else can I do? K equals 1 will give me radius square root of 8. I don't feel like graphing that. Well, now maybe we can do it because I don't have any units drawn. So this will be k equals, oh, that was, sorry, I meant to do k equals 2 first. K equals 2 is going to give us the square root of 5 as radius. That'd be for k equals 2. K equals 3, sorry, k equals 1, I'm trying to go backwards. K equals 1 will give us square root of 8 as the radius. So it's not going to be quite twice the radius. Maybe something like this. Imagine that these are all concentric circles. They look okay. And then for k equals 0, that's the last integer value we can pick. We'll get a radius of 3, which is the square root of 9. So it's going to be just outside of that one. Okay. So by the way, I'm recording the heights. Those k values are the heights. So you can see that if we were looking straight down at this 3-dimensional graph, we would be looking at the top of a hill that slopes down in every direction until it hits height 0 on the outer circle of radius 3, and then there are no level curves below that. So this is just sort of a dome or a cap or a perfectly semi-spherical hill. And those are the level curves. So let's use this graph and use our knowledge of level curves to answer the second question, which is what direction does the gradient point? We just learned a few slides ago that the gradient always points in the direction of maximal increase. So if we sketch our point 1, 2 in the picture, I'm going to put it in dark blue. Let's see. Let's try to get this more or less accurate. So, if I plug in 1, 2 into the function, I'll get, let's see, 9 minus 1 minus 4. That's going to be a radius 2. So the radius 2 circle was the one. I don't know if we had one on there. Let's see, square root of 4. That's going to be right in here, actually. The k value is not an integer, but and then if we go 1, 2, that's going to be somewhere up here. Just trying to be as accurate as possible. This is our point 1, 2 that we're looking at. And what's the direction of maximal increase? Well, it's going to be in plain English terms, straight up the hill towards the peak. And in vector terms, it's going to be a vector pointed straight at the origin. I was trying to do that in different color. Let me do it one more time. So nabla f, our directional derivative, our gradient vector is going to point straight towards the top of the hill, which in our figure is the origin. Again, this is because we learned algebraically that the direction of maximal increase is in this direction, and the fastest way to go up a hill is to go straight towards the top, no matter where you are on the hill. Part C of this question is asking, without doing any calculations, can we just use geometry and draw a careful figure, but not calculate anything, to guess if the rate of change along that given vector 0.6, negative 0.8 is positive or negative? And intuitively, this is asking if this directional derivative or the rate of change of the function as we move along this vector being positive or negative is asking, are we walking uphill or downhill if we walk in that direction from the point 1, 2 that we started on the side of the hill? And you can imagine this being really good for cartography and for surveying and other sorts of real world problems where we actually have literal topography, but it can be also useful in situations with more abstract multivariable functions. So let's work this out. How do we know if this directional derivative is positive or negative? Well, before I sketched in the picture, just to remind you, our directional derivative had a few different formulas. There was a limit formula, there was a dot product formula, and there was also an angle formula. I'm going to use the dot product formula, but keep in mind it's related to the angle formula, where if I take the dot product of the gradient vector at our point, which I've drawn here pointing straight towards the origin, straight to the top of the hill, and our vector u, then that dot product will tell us if the angle between those two vectors is acute or obtuse. We're actually going to use that to answer the question. So is this directional derivative positive or negative? The dot product will be positive, and therefore the directional derivative will be positive if the two vectors form an acute angle, and it'll be negative if they form an obtuse angle. This is a bit of a review from a previous section, but let's just carefully draw our vector 0.6, negative 0.8. If I travel 0.6 units in the positive x direction and then down by 0.8, the vector is going to look something like this. And it may not be, let me actually draw it in blue. It may not be exactly on the same level curve, so let me just exaggerate the coordinates a little bit, but it'll go to the right and down, and that's the important thing here. Moving to the right and down will form an acute angle theta with the gradient vector purple pointing straight towards the top of the hill. And since it's acute, this dot product has to be positive, and therefore our directional derivative has to be positive. So without even calculating anything, just knowing geometrically which way the gradient points, we can plot our path or plot our direction to travel and know that we are traveling uphill. The rate of change of this function is positive. And you might not be able to tell that even if you were in person standing on the side of the hill there. Sometimes, the side of a grassy hill could play tricks with the eye, and it might look like you're slightly walking uphill when you're actually walking downhill or vice versa. In this case, using geometry, we know using the dot product that we're traveling uphill if we walk in this direction. Although it might be a little slower, it might be easier on the knees to take this path. Let's finish the question. There was a part D to answer, and I've copied the function and that direction so we can answer this. We want to calculate, first of all, the gradient and then use it to calculate the directional derivative in this direction. Let's see how fast we're traveling uphill in that direction. So to compute the gradient, we need the components are the partial derivatives of the function. And here's our function. If I quickly compute a partial derivative with respect to x and y using the chain rule, I'm going to get, let's see, x over the square root of 9 minus x squared minus y squared, and y over the square root of 9 minus x squared minus y squared. If you weren't sure how I got those, of course, I skipped some steps that I didn't say out loud. Pause the video now and double check that you can compute these partial derivatives. So we want to compute nabla of f, the gradient vector of f, at 1, 2. So this is a vector whose first component is, we're going to plug in 1, 2 into the x partial derivative. So there's a 1 in the numerator. Let's compute the whole denominator for x, xy equals 1, 2. This is going to be 9 minus 1 squared minus 2 squared. That's 9 minus 5, which is 4, which is going to be square root of that is 2. So the denominators are always 2. The numerators are given by x and y. So this is actually pretty easy to compute. Now that we know that, so let's just hold on to that if we need it later. X is 1 and the denominator is 2. So the x component of the vector is 1/2. Y is 2 and the denominator is 2. So the y component of our gradient vector is 1. So 1/2, 1 is the directional vector of maximum increase. It points straight at the origin. And if I told you point a vector straight at the origin from the xy point 1, 2, you probably could have used basic geometry to figure out the components of that vector. Although you may not have known the length of the vector, you certainly could have figured out the line that passes from the passes through the origin in this point and used slope to come up with a directional vector. In this case, we actually directly solved for the vector of maximal increase whose length will compute that amount of maximal increase. So let's compute, for now, just the directional vector along that other vector, 0.6, -0.8. But you can also compute the magnitude of this, or the length of this, will give you the maximum rate of change, or the maximum altitude change, if you think of it that way. Great, so to compute the directional derivative for this other vector, 0.6, -0.8, we're going to take the gradient vector at 1, 2 and dot it with this directional vector. The gradient vector we just computed to be 1/2, 1. And sorry, I feel like I did something wrong. I'm missing minus signs. That is good to record. So I actually have a -1/2 and a -1. And I just want to pause and comment on how I caught that halfway through the problem. I just started thinking about geometrically what these two vectors would look like and what the angle between them would look like, since we computed, or we observed it to hopefully be an acute angle so that this directional derivative turns out to be positive. And then I was thinking, well, if we draw this directional, this gradient direction, 1/2, 1, that's actually pointing further away from the origin, not towards the origin. So I think I had something wrong. Then I observed that when taking the partial derivative and doing the chain rule, I missed a minus sign for each of the x and y variables as part of the chain rule. So hopefully you actually paused the video and caught the correct version here. But in any case, our direction vector for the gradient is -1/2, -1. Our direction vector we're trying to compute a rate of change along was 0.6, -0.8. And to compute the dot product, we're going to have -1/2 times 0.6 minus 1 times -0.8. And we'll just do this in decimals. So half of 0.6 is 0.3. It's -0.3. The minuses cancel out and get 0.8. This gives us 0.5 or 1/2 as our directional derivative in the direction of that vector. I also encourage you as an extra exercise to compute the length of the gradient vector to find out the direction, or the amount of maximal increase, the maximal rate of change of this function, pointing straight towards the origin. Okay, we'll have one more example to do in a moment. Let's switch back and learn a little bit more about applications of the gradient vector and directional derivatives. I'm going to leave this one as an exercise for you to do, but as I've been saying pretty much the whole video, we can use topographical maps and the height of a function as literal altitude off of sea level to model our gradient vector and our directional derivatives. So at each of the labeled points, A, B, and C, as an exercise, I want you to draw the vector nabla h, that's the gradient vector at each of those points. And to do so, you'll have to estimate what the x and y components are of the vector. I also want you to label or exaggerate the length of these vectors to show which of the three vectors, the gradient vectors at A, B, and C, will be longest and shortest, and then there's one left in the middle. So they're all going to point in different directions, and you can use either or any of the 3 or 4 definitions of the gradient vector we have to define this, but I also want you to think about which is the longest and the shortest in terms of rates of change of this function. That one's going to be an exercise. Here's another application to keep in mind. And gradient vectors and directional derivatives show up all over the place in numerical analysis and any place where we have multivariable functions. So edge detection is a type of technique involved in image recognition. We talked a little bit about image recognition already in our vector chapter. And here we can apply our knowledge of rates of change to study how images change pixel by pixel or coordinate by coordinate. The length of the gradient, let's say of the brightness function in our black and white image detecting function, can detect the edges of a picture because the brightness changes most quickly at the edges of the picture. And even more granularly than that, for certain types of objects in a picture, like for example, this, if you kind of pull your head away and look from a distance, this looks like a human eye. You can see that certain parts of the eye, the retina versus the sclera, for example, will have different contrast, or will have large contrast in their different amounts of brightness. And you can use this type of identification, or rather a computer system can use this type of identification to describe the boundaries of different objects of varying colors. We can identify the boundary of a particular figure in the picture, and we can also identify the boundary of the figure if it's the boundary of the picture itself if it's not if it's not cropped in a certain way. So if the brightness function is capital B and we measure the following partial derivatives of the brightness function in each of the x and y directions, then and you can actually do this explicitly if you have the function, or if you have a table of values of brightness at each pixel, then these two partial derivative values thrown into the components of a vector will give you the value of the gradient vector at this point. And we've drawn the gradient vector at a couple different points here. For example, at the pixel 336, 785, which is a part of the sclera of the eye, it looks like, or the white of your eye. The brightness vector, or the gradient vector for brightness is -2, -8. If you compute the gradient vector at a different point, namely the one on the boundary of this eye, you'll see that the gradient vector has much larger components, in this case, -42, -67. And keep in mind that each of these vectors is pointing in the direction of maximal increase of brightness. So if you're already in a bright region, you expect to not have to travel very far towards regions with higher brightness. Whereas if you are in a lower brightness region. And if you're still on the boundary of the eye, if you're just on the dark side, you're in a region of lower brightness, then you should expect a longer gradient vector to tell you to travel in this direction and travel uphill faster. The length of the vector will be highest when there's contrast between bright and dark regions. So it's really the length of the vector that's interesting to us for this particular question. But it also helps you identify geometrically the different regions, because we will be pointing towards regions of higher brightness. And as we said earlier in the video, the brightness gradient vector will be perpendicular to the level curves. And the level curves will help you describe increasing and decreasing regions of brightness and darkness, and level curves in general should be capturing the boundary of certain regions, like the edge of the eye could be captured by a certain brightness level curve. So all of these things you can use in computer detection, or rather image recognition systems with a computer to study the brightness function in this way. And it can help computers that are trained on large data sets to become proficient at identifying human eyes versus non-human eyes, or other types of shapes that can be quantified in large data sets. So this is just one piece of the tool set that computer scientists use to program these types of things. Let's do one more example. I promised a new formula for the tangent plane to a surface, such as x squared plus y squared plus z squared equals 14 at a given point. We already know a few ways to do this by computing the, well, we know one way to compute the tangent plane by computing the partial derivatives with respect to x and y. And in this case, we haven't solved for z, so we have to do a little more work using implicit differentiation to solve for those partial derivatives. Once we have those partial derivatives, those give us the mx and my slopes, and we can write out a formula for the tangent plane that way. In the previous video, with no reference to tangent planes, but just planes and higher dimension hyperplanes and any number of variables, we learned about the normal equation for such a structure. And in 2 dimensions, or really in 3 dimensions here with 2 input variables, the tangent plane will have a normal direction and a normal vector we can compute to write a different formula for the tangent plane that we've done previously. We're going to see that this connects back to everything we've been discussing so far. So let's try to do this problem ourselves. By the way, I'll leave it as an exercise to practice the old-fashioned way. For us, the old-fashioned way is compute the partial derivatives of f. And sorry, here's the function. Compute the partial derivatives of f if you're able to solve for a function z equals f of xy that contains the point 2, 1, f of 2, 1. And if you're able to do that, you can explicitly write out the tangent plane using our classic way of doing it. But I'm going to teach you a new way of doing it that doesn't require a function little f solved for x and y, or rather z equals some function just of f of x and y, but rather treats this entire expression as a level set of some free variable function, capital F of x, y, z. So the key insight here is that the formula x squared plus y squared plus z squared equals 14 is secretly taking a 3 variable function, capital F, shown here, and setting it equal to 14. That's taking the level set, now it'll be a level surface, not a level curve, to that 3 variable function. We have only talked about the gradient in detail for functions of 2 variables, but all of the same properties we learn will hold in higher dimensions. And in particular, the gradient vector, nabla of capital F, will be orthogonal to each of the level sets of the 3 variable function set equal to any height. So each level set, for example, the surface that we're looking at, set equal to 14, is or has an orthogonal vector given by the gradient vector, and being orthogonal to the surface, or that level set, is the same thing as being orthogonal to its tangent plane at any given point. So I'll write it as the vector n, but we'll compute it using the gradient formula. N will be a normal vector to the tangent plane at any point on our surface. And in particular, let's compute the gradient of this capital F. Now that we've solved for a single function, capital F of x, y, and z, we can treat each of these as variables, and we'll have 3 components of our gradient vector. So in general, this will look like the partial of capital F with respect to x, y, and z. Those will give us each of the 3 components of this gradient. I'm going to save a bit of space. We can compute it at the point. Let's see. No, I'll do it below. This is fine. So our function is x squared plus y squared plus z squared. This turns out to be pretty easy to compute each of the partial derivatives for. It's just going to be 2x, 2y, and 2z. And if you weren't sure about that, pause the video and just make sure that you can compute all three partial derivatives of this function of three variables. Now that we have our gradient vector, we know that plugging in any point on the surface, x comma y comma z, will determine a normal vector to the tangent plane to the surface at that point. So to write down the normal equation for the tangent plane, we need a normal vector, and we're going to use this formula and plug in x, y, and z to find a normal vector. And we need to dot it with x minus x naught, y minus y naught, and z minus z naught. And the normal equation says set this dot product equal to 0. This is any point, or sorry, any vector lying in the plane, and it's orthogonal to a normal vector. And in particular, we know a point on the plane already that will give us our x naught, y naught, and z naught coordinates. And this will give us our full formula. So we have two pieces left to do. At the point x naught, y naught, z naught that's given, which I need to scroll up to remember, it was 2, 1, negative 3. Those are the three coordinates we'll plug in here, but we also need the normal vector. So the normal vector is going to be the gradient vector at this triple, which is just double all of the coordinates. So 4, 2, negative 6. And finally, to write down the equation for the tangent plane, we're going to put all of this information together. So we have 4, 2, negative 6 dotted with, should really have angle brackets up above, x minus 2, y minus 1, z plus 3 is equal to 0. This is the vector dot product form of the equation. We can also expand it out as 4 times x minus 1 plus 2 times y minus 1 minus 6 times z plus 3. And I'll leave it to you to rewrite this just with 4x plus 2y minus 6z plus or minus some constant equals 0. That's the linear form we've used in the past for the normal equation. Great. There's a couple things left that I want to wrap up. So this is really a main idea to summarize a lot of what we've learned about tangent planes so far and how it relates to directional derivatives, gradient vectors, and rates of change in this video. So if we have an equation describing some surface in 3 dimensions that we can't necessarily solve for a function, but we still want to write the equation for the tangent plane at a given point to that surface, we can treat the graph of that implicit equation as the level set of some function. For example, capital F equals x squared plus y squared plus z squared was our 3-variable function in the previous example. Treating this as a level set of a function means that the gradient vector at any point is orthogonal to that entire level set, and in particular is orthogonal to the tangent plane at any point in the level surface. Once we know that, we can compute the gradient vector at any point to determine a normal vector and write down the normal equation for the tangent plane quite easily because we already know the point that we're plugging in. By the way, you can do this in 2 dimensions when you have a function f of x of a single variable and get an equation for tangent lines in just the same way. If we have only a single variable's worth of input, then the gradient vector in that case will only be a single number equal to the value of the single derivative of the function at that x value. But nevertheless, that still has a normal equation attached to it. And you can treat things as level curves of some 3-variable function and compute things explicitly that way to get an equation for a tangent line. It's going to look similar to our normal equation for the tangent plane. And this is pretty robust in any dimension. Here are some summary questions to leave you with. And I encourage you to go compute some directional derivatives on your own. Choose a function, choose a directional vector, find a unit vector in that direction, and then practice computing. We'll do some of these in class, but here's some summary questions. What does the direction of the gradient vector to a function tell you? If we pick a direction and compute a directional derivative of a function, what does this mean geometrically? And if we want to compute a directional derivative, what are some different ways of computing? Finally, how is the gradient vector related to a level set of a certain function? That's all I have for now, so thanks for tuning in, and I'll see you next time.